An observer can cross this entire body in under 15 minutes. This is a factual measurement, as Bennu possesses a diameter of approximately 490 meters. These dimensions are smaller than Central Park, many urban districts, or standard international airport runways. The highest topographical point offers a nearly unobstructed view of the entire asteroid. Despite its size, it constitutes an independent celestial body, approached by spacecraft at speeds slower than a descending elevator. Sudden kinetic movements risk permanent ejection into space. Local microgravity causes an 80-kilogram mass to register a weight lower than a single sheet of paper. Applying the mechanical force required to climb a standard Earth stair-step results in permanent surface departure. The asteroid completes a full rotation every 4 hours and 18 minutes. A local solar cycle concludes in less time than a standard feature film. The sun rises, transits the black sky, and sets within a few hours, lacking an atmosphere to scatter radiation. The sky remains entirely black even at midday, as the non-uniform surface becomes visible beneath a descending spacecraft. The terrain lacks the fine dust characteristic of the Moon, presenting instead a chaotic distribution of boulders, some equivalent in size to automobiles. Larger formations match the dimensions of houses, with the largest cataloged rock measuring approximately 55 meters, comparable to a football field's length. The OSIRIS-REx mission encountered massive structural blocks rather than the expected fine sand. Bennu is classified as a rubble pile rather than a solid monolith. The structure consists of unconsolidated debris held together by weak gravitational forces. This structural model resembles the debris of a demolished building gathered into a spherical shape. Formation occurred over 4 billion years ago during the early stages of the solar system. At a descent altitude of 20 meters, the asteroid's curvature becomes clearly visible. The horizon limit sits mere hundreds of meters away, confirming the body's small scale. Temperatures on the illuminated side can exceed 120 degrees Celsius, sufficient for rapid water vaporization. Unlit regions experience drops to approximately -70 degrees Celsius, capable of freezing exposed fluids instantly. This extreme thermal variation occurs within hours before a spacecraft touches the surface with negligible impact. There is no dust displacement comparable to lunar landings, no wind, and an absence of sound. During the OSIRIS-REx sampling maneuver, the spacecraft's arm unexpectedly penetrated nearly half a meter into the yielding material. The regolith offered no structural resistance, meaning physical contact registers as a mere touch without measurable weight. Incorrect kinetic impulses cause ejection, as Bennu's escape velocity is approximately 20 centimeters per second. This metric is slower than an infant crawling, requiring strict observational awareness. The entire body fits within a single field of view, displaying an equatorial ridge formed by the asteroid's relatively rapid rotation. Rotational forces slowly shift material toward the equator, creating this prominent structural bulge. The surface color is exceptionally dark, reflecting less light than coal. Physical samples appear nearly absolute black under direct observation. Hydrated minerals exist within these rocks, indicating chemical interaction with water on the asteroid's parent body. Carbon-based organic molecules, fundamental blocks for biological chemistry, have also been detected. The material present predates the formation of Earth itself. These fragments survived billions of years of collisions, solar heating, and cosmic bombardment. The structure lacks complete stability, with documented observations of spontaneous small particle ejections into space. The asteroid exhibits active movement mechanics. Surface locomotion translates directly into orbital mechanics, establishing primary exploration parameters. Pushing off the surface with standard terrestrial walking force results in permanent ejection. This establishes the primary survival protocol on Bennu. Microgravity converts simple locomotion into a strict negotiation with physical laws, where a toe push initiates a slow space trajectory. Complete gravitational escape requires merely 20 centimeters per second. Standard Earth jumps easily exceed this velocity, leading to floating rather than stepping. Movement demands specific techniques: short dragging steps, bent knees, and a lowered center of mass. The process mimics astronauts moving in slow motion. The ground consists of accumulated fragments spanning billions of years. Loose stones, stacked blocks, and fine particles intermix with car-sized rocks, eliminating traditional solid ground. The OSIRIS-REx spacecraft touched the surface for mere seconds. Despite the brief contact, it sank nearly half a meter before firing thrusters to avoid regolith engulfment. The structural behavior resembles a box of loose debris rather than a compact rock. Moving a stone with a foot produces non-terrestrial reactions. Displaced objects slide slowly with minimal resistance for several seconds, while lofted particles remain suspended. These particles enter short, curved trajectories before settling. The asteroid completes a full rotation in slightly over 4 hours. Consequently, the entire terrain visibly rotates beneath an observer moving just a few meters. Equatorial rotation actively reduces local gravitational forces. This dynamic compares to standing on a slow-moving, world-sized carousel. At the equatorial ridge, measurable weight is lower than in polar regions. Centrifugal forces counteract natural gravity, leaving rocks resting at the edge of escape parameters. Testing a larger displacement requires minimal impulse. A slow ascent lacks the sensation of falling or sudden acceleration, resembling underwater movement without fluid resistance. The horizon's curvature exposes nearly half the asteroid simultaneously. This brief suspension constitutes an official orbital state before a slow descent begins. Dropped tools require several seconds to reach the ground, making simple activities highly precise operations. Equipment assembly demands anchoring, and all tools require physical tethers. An incorrect push sends objects into permanent solar orbit. The lack of atmosphere allows sand-sized micrometeorites to strike the surface at extreme velocities. These impacts displace particles, contributing to spontaneous fragment releases driven by extreme thermal cycling and rock fracturing. The short 4-hour diurnal cycle triggers rapid temperature shifts. Intense solar heating followed by drastic shadow cooling creates structural fractures and fragment detachment. The surface stability is constantly compromised by weak gravity and continuous physical transformation. The circumferences remain small enough for foot traversal. However, environmental hazards exist within every meter. Locomotion here equates mathematically and physically to flight dynamics. Bisection of the asteroid would reveal a lack of a solid core. The interior consists largely of empty space. Scientific classifications label Bennu a rubble pile rather than a dense meteorite. The structure comprises gathered building debris, large blocks, medium fragments, and fine dust held by weak gravity. Average density measurements marginally exceed that of water. This data contrasts sharply with the naturally higher density of its constituent rocks. The density deficit confirms significant internal voids between structural blocks. Analytical models suggest up to 20% or more of the internal volume features pores and cavities. Consequently, Bennu maintains a partially hollow architecture. This internal porosity explains the OSIRIS-REx sampling arm penetrating the soil like granulated foam. The ground yielded entirely without rigid resistance. Construction or drilling operations cannot rely on subterranean compaction, demanding slow monitoring. Excessive mechanical force risks displacing entire block formations. Cataloged rocks include specimens measuring 30 meters, surpassing residential buildings. These massive objects rest on smaller blocks rather than anchoring into bedrock. The landscape represents an accidental architecture built through billions of years of collisions. A single significant impact holds the potential to alter the entire topography. Gravitational reassembly of fragments from an ancient collision formed this imperfect sphere. Soil granularity spans from fine dust to basketball-sized stones. Cohesion relies strictly on weak gravity and minor electrostatic forces. Solar radiation in a vacuum environment induces electrical charges on particles. These charges cause fine grains to exhibit slight attractive or repulsive behaviors. The surface registers simultaneously as solid and physically unstable. Applied foot pressure causes minimal terrain adjustments, behaving unlike sand or concrete. The material acts as a slowly reorganizing fragment field. Internal porosity dictates the asteroid's external morphology. The equatorial elevation formed through gradual internal material migration driven by rotational mass redistribution. Over millions of years, rotation forced particles toward the equator, creating an accumulated midline. Small impacts generate craters and simultaneously reorganize internal structures. Minor object collisions send vibrations through the body, shifting internal block arrangements. Bennu operates as a dynamic entity rather than a static relic. Internal pockets of compaction and high porosity have likely shifted multiple times since formation. Stable zones contrast with areas acting as structural debris traps. Surface depressions lack the defined edges characteristic of classic craters. Loose material slowly slides to partially fill holes, smoothing crater morphologies. Geological mechanics rely strictly on microgravity and debris reorganization, lacking tectonic or erosion forces. Every rock originated from a larger parent body existing prior to Earth's habitable phase. The terrain constitutes a regrouped cosmic debris field. Bennu is not an inert stone positioned in a vacuum. The structure maintains a delicate equilibrium subject to continuous readjustment. Unlike worlds defined by volcanism or seismic activity, Bennu ejects rocks directly into space. This phenomenon is a documented observational fact. The OSIRIS-REx mission directly recorded this activity in 2019. Particles ranging from coin-sized elements to larger fragments detach and accelerate slowly away from the surface. These ejections occur without audible sound or visible explosive triggers. Fragments lift off from illuminated sectors as if propelled by invisible physical forces. Specific particles achieve terminal velocities exceeding local gravity, while others enter temporary orbits before surface re-entry. The physical mechanism mimics debris respiration. Thermal shock stands as the primary scientific explanation. Direct solar radiation pushes surface temperatures above 100 degrees Celsius during the short day. Nighttime conditions rapidly drop these values far below freezing. This extreme, rapid thermal cycling induces severe mechanical stress on rock formations. Repetitive expansion and contraction create fractures, causing fragment detachment. While terrestrial gravity pulls such fragments down, microgravity allows them to enter flight trajectories. Small particle jets detach from illuminated equatorial regions. Low escape velocities ensure that fragments moving slower than a residential vehicle permanently leave the asteroid. Multiple ejection events were recorded throughout the mission timeline.
This behavior classifies Bennu as a specifically active asteroid. The body lacks sublimating ice or atmospheric layers found on comets, yet maintains active particle ejection. Environmental instability extends beyond weak gravity. Unshielded micrometeorite impacts also trigger structural rearrangements and fragment launches. The vacuum eliminates deceleration, turning microscopic impacts into high-velocity micro-explosions. Ejected particles transit slowly above the horizon line. Low velocities permit visual tracking of their trajectories over several seconds. These ejection patterns provide critical data regarding internal cohesion. Easy fragment detachment confirms the rubble pile lacks structural binding. Rocks rest upon each other without fusing. This challenges traditional models of asteroids as solid monolithic blocks. The reality involves fragile agglomerates adjusted continuously by minimal physical forces. Fallback trajectories deposit particles in new regions, establishing an ongoing surface recycling process. Ancient materials redistribute continuously, partially filling existing depressions. The navigable dimensions host highly complex physical transformations. The ground structure remains impermanent, subject to shifts and fragmentation. The environment constitutes an active kinetic system despite its sub-kilometer diameter. All mechanical alterations proceed in an absolute vacuum, absent of wind or acoustic signatures. Movement occurs slowly against the deep space backdrop.
A specific latitudinal band exists where rotational forces actively counteract gravitational limits. This region represents the zone of maximum structural instability. The equatorial ridge forms an irregular elevation of piled blocks, angled fragments, and fine accumulated material. The rotation completes in slightly over 4 hours, forcing rapid circular transit for equatorial coordinates. This rotation generates a measurable centrifugal force. Unlike Earth, where high mass nullifies rotational sensations, Bennu's microgravity amplifies the effect. Centrifugal mechanics actively reduce the downward gravitational attraction at the equator. The physical outcome simulates a body slowly dismantling its own structure. Navigational steps require absolute discipline, as minimal impulses result in exaggerated lift. Surface contact registers purely symbolically. Released tools bounce lightly without immediate return. Objects float momentarily, governed by competing kinetic forces. Eventual surface return occurs mere centimeters from the initial drop point. Escape velocity at the equator aligns with the speed of an extremely slow terrestrial walk. Careless kinetic movement converts objects into temporary satellites. The ridge's formation resulted from millions of years of particle migration. Impact-induced internal vibrations force loose material to slide toward the equatorial midline. The process mimics granular accumulation at the widest point of a spinning object. Massive blocks positioned precariously, often balancing upon smaller fragments. The lack of atmospheric erosion preserves these structures. Simultaneously, microgravity ensures no formation is permanently anchored. Minor rotational acceleration could trigger equatorial detachment. The Yorp effect
drives long-term rotational shifts via solar radiation absorption and re-emission. This thermodynamic exerts continuous microscopic torque on the asteroid. Over millions of years, the Yorp effect alters the overall rotational velocity. Future acceleration could lead to significant equatorial mass loss into space. Navigating this zone means walking along a line of cosmic physical equilibrium. The abrupt sunset rapidly eliminates solar illumination due to the vacuum environment. Thermal contraction accelerates fracturing, creating loose fragments highly prone to equatorial escape. The structural integrity remains inherently fragile. The asteroid is ancient enough to date planetary formation, yet remains actively engaged in physical reshaping. The ground material actively migrates beneath surface operations. Exploration involves walking atop an architecture existing on the absolute boundary between cohesion and dispersion. This boundary manifests precisely along the equatorial ridge.
Direct physical traversal, microgravity interaction, and ejection observation leave a fundamental structural question. The core mechanisms holding the debris field together require analysis. A solid composition would yield a significantly higher overall density. Volumetric measurements confirm Bennu is far less dense than standard terrestrial rocks. This data mathematically requires the presence of vast internal voids. Studies indicate a considerable fraction of the interior volume comprises pores and cavities. The structural model mirrors a stone sponge, neither entirely hollow nor solid. This internal architecture dictates the asteroid's dampening response to external kinetic impacts. The OSIRIS-REx sampling arm penetrated the loose outer layers deeply without meeting rigid bedrock. Surface materials float functionally above unconsolidated internal strata. Drilling operations would transit multiple fragment layers with no guarantee of encountering a compacted core. The interior likely features large blocks separated by extensive pockets of fine material. This porous configuration actively enhances the asteroid's long-term orbital survival. Despite measuring under a half-kilometer and representing a volume smaller than urban districts, it has endured billions of years of cosmic impacts. Structural fragility provides paradoxical mechanical strength. While solid monoliths fracture violently under kinetic strikes, a porous agglomerate absorbs energy by redistributing internal tension. Impact vibrations reorganize internal block placements without shattering the parent body. The entire structure functions mechanically as a cosmic dampener, while sample analysis reveals another critical factor, the presence of hydrated minerals. This chemical signature proves the original parent body interacted directly with chemically bound water during the early solar system. Surface blocks contain chemical records of environments present during primary planetary organization. These geological components predate terrestrial oceans and biological evolution. The ancient fragments rest unanchored, held by gravity so weak that minor mechanical force could displace them. Internal void mechanics drive surface phenomena, including the equatorial ridge formation, mass redistribution, and particle ejection. The structure confirms an adaptable, non-rigid architecture. Surface traversal means engaging directly with the physical memory of planetary formation. The asteroid remains a primordial fragment surviving the solar system's initial chaotic phases. It is compact enough for pedestrian transit, yet complex enough to secure fundamental chemical data. Its fragility demonstrates the relative nature of cosmic structural stability. A new solar cycle initiates every 4 hours, illuminating a world devoid of atmosphere or oceans. Billions of years of geological data reside within a diameter of under 500 meters. Inhabiting this space requires existing upon a direct remnant of the deepest solar system history. A complete circumnavigation of this body can occur before an evening meal. Bennu's perimeter measures approximately 1.5 kilometers. A slow, controlled pace allows a full circuit in under an hour. The extraordinary nature of this transit involves more than just distance. The ground itself rotates beneath the observer. A complete rotation concludes in 4 hours and 18 minutes. During a surface walk, the sun alters its position visibly against the black sky. The absence of an atmosphere eliminates light scattering, blue hues, and twilight phases. Solar appearances are abrupt and darkness is absolute immediately after setting. Walking near the poles offers slightly higher gravity than the equator, making displacement marginally more predictable. Movements remain short and calculated, akin to crossing thin ice. The tight curvature causes the terrain to drop visibly within a few hundred meters. The geometrical experience compares to walking across the roof of a spherical stadium. Forward progression reveals varying rock sizes and compaction levels. Specific zones feature fields of giant blocks with over 200 rocks exceeding 10 meters documented. Some structures match 3-story buildings, while the largest extends 55 meters. These formations rest without cementation, relying on minimal gravity susceptible to landscape-altering impacts. Approaching the equator reveals an elevated ridge encircling the asteroid. Rotational dynamics slowly shift material toward the center to build this feature. The process reflects centrifugal material accumulation. Rotational force severely diminishes local gravitational effects at the equator. Specific coordinates register practically zero downward attraction. An exaggerated impulse initiates long, slow surface trajectories. A minor jump results in an unintended high ascent while the world rotates underneath. The physical state registers as suspension rather than falling, offering a simultaneous view of the entire body. Descent concludes with an extremely soft surface touch. Direct solar light presents intense white radiation without atmospheric filtration. Surface temperatures rapidly absorb heat, reaching water-boiling parameters. Conversely, immediate cold dominates the shadows of large blocks. Thermal gradients between illuminated and shadowed sectors are extreme. Soil temperatures transition from extreme heat to freezing conditions within hours. Rapid thermal cycling fractures rocks and detaches fragments, confirming the asteroid's non-static nature. Structural transformations happen during every rotation. Exploring half the perimeter highlights the paradox of a world too small for navigational loss. True distance metrics do not apply. Earth horizons conceal continents, whereas Bennu's hide mere hundreds of meters. This dark fragment contains material predating terrestrial mountains. The composition includes hydrated minerals and organic compounds from the solar system's inception. A complete foot traverse of the world concludes. The visible surface represents merely the outermost layer.
You walked on it. Now you must look outward. Asteroid Bennu is not an isolated rock drifting aimlessly in darkness. It follows an orbit around the Sun that regularly crosses Earth's orbital path. Roughly every 14 months, it completes a full journey around the Sun. During some of those cycles, it passes relatively close to Earth. Close, in astronomical terms, still means millions of kilometers, safe distances. But the orbital intersection is real. And this is where precision matters. Asteroid Bennu measures roughly half a kilometer across, about the length of 5 football stadiums placed end to end. In space, That may sound small. On Earth, it is enormous. Its mass equals hundreds of millions of tons of rock loosely bound together by weak gravity. If an object this size were to impact Earth, the energy release would be equivalent to thousands of nuclear explosions detonating simultaneously. It would not cause global extinction like the 10-kilometer asteroid that ended the age of the dinosaurs. But it could devastate a region the size of a large country. An ocean impact could trigger massive tsunamis. A land impact would excavate a crater several kilometers wide. Shockwaves could shatter windows hundreds of kilometers away. And yet, the probability of impact in the next century is low. Extremely low. Current orbital calculations indicate that during its most significant future close approaches, particularly late in the 22nd century, the chance of collision remains small. Not zero in absolute mathematical terms, but statistically remote. Why is there any uncertainty at all? Because space is dynamic. Asteroid Bennu is influenced by Earth's gravity, by Venus, and even by distant Jupiter. Each close pass subtly adjusts its trajectory. But there is an even more delicate force at work: sunlight. When solar radiation heats Bennu's surface, the asteroid absorbs energy and later re-emits it as heat. That re-emission is uneven. The result is a tiny thrust, almost imperceptible, that slowly alters its orbit over time. Imagine a constant gentle breath pushing a drifting object day after day. A change in speed smaller than a walking pace, sustained for decades, can shift its position by thousands of kilometers in the future. That is why asteroid Bennu is one of the most precisely tracked objects in the solar system. It is not just a rock. It is a measurable future.
You have stood on its loose surface, felt its gravity weaker than a playground jump, watched it spin once every few hours. Now imagine that entire body traveling through space at tens of thousands of kilometers per hour. That is the true scale. Bennu is not heading toward us. It is simply following its natural path. But for the first time in human history, we know where it will be decades from now. We know its density. We know its structure, a rubble pile body filled with voids. We know how sunlight slowly nudges its orbit, and that knowledge changes everything. If intervention were ever required, it would not demand destruction, it would require time. A small spacecraft striking it gently, a gravitational tug applied years in advance, a slight alteration in velocity, no more than the speed of a slow bicycle, applied early enough to shift its future position completely. The secret is not force, it is anticipation. You completed your journey around asteroid Bennu, understanding its surface, its fragility, and its ancient origins. Now you understand its significance. It is a relic of the solar system's formation, a fragment older than Earth's oceans, a body that quietly crosses our orbital neighborhood, not as a villain, but as a test of whether humanity can observe, calculate, and act long before danger becomes catastrophe. Asteroid Bennu continues its silent rotation, and now, unlike any civilization before us, we are watching.